Today we're going to start Chapter 6 on the momentum equation. This chapter is really just applying the Reynolds transport theorem to momentum. Just as in Chapter 5, when we developed the Reynolds transport theorem and we applied it to mass, this chapter we're going to apply it to momentum. And it will allow us to solve a whole new series of problems in fluid dynamics. So in this first section, it's quite a short section. We're just going to go really quickly through a couple of things, define what we mean by body and surface forces, state what Newton's second law is, basically F equals ma, and also just briefly describe to you that the book illustrates something called the visual solution method, which I really think is something very similar to just drawing force diagrams. But I'll just draw your attention to the book, and if you're interested in looking at this visual solution method more, you can refer to the textbook. So let's jump right in. So the book describes that in order to understand Newton's second law of motion, it's important to understand the different types of forces that we might have. Find in different problems that we might have to solve. And the first, it states about surface forces, and these are forces where the things have to be in contact, have to be in physical contact. And the book gives an example of air flowing over an airplane wing and basically providing lift. That lift is caused by a force of the wind on the wing of the airplane, and so the air is coming in contact with the airplane wing, and so that would be considered a surface force. And we can see that these are important for solving both problems in both fluids and in solids. And so some examples of some surface forces pressure that are of importance to fluids are pressure forces, which we've talked about, shear forces, buoyant forces, which we've also talked about, surface tension forces, but also lift, drag, and thrust forces. And then in solids, you've been exposed to these in some of your other classes: frictional forces, tension, applied force, spring force, and support forces. Other forces, another category of forces, are body forces, and these are forces that don't require physical contact between the interacting bodies. The main one that we're familiar with is the force of gravity, which is acting on basically each particle or each molecule, for that matter, anything with mass inside of our body that we're considering. And then, of course, magnetic and electric forces also act at a distance and don't require contact. So moving on, Newton's second law of motion we're pretty familiar with is just that some of the forces, external forces here, are going to basically have to be equal to the mass of the object that under consideration, the mass of a particle, and its acceleration. So if there's any imbalance of force on this mass, it will accelerate, and this is something we should be quite familiar with. And the book describes something called this visual solution method. Really, I look at this as just being a way of writing out, basically kind of pictorially, drawing a picture, drawing some forces. So here's a top view of this airplane that's turning in a curved path, and it's accelerating towards the center because it's on this curved path. We've seen that before. Whenever something is curving, it's actually has an acceleration inward. And looking at the plane from a front view, we can see that drawing a diagram of forces, we have the weight force here, as well as some lift that's occurring because of the wings. And it might not be quite obvious that how these forces all fit together, but when we actually draw them on a diagram here, we can see that the resulting force of adding both the lift tip to tail here, adding the weight to this lift vector, gives us this resulting vector here. And so we can, this visual solution method takes these pictures, and you can then write down the forces from those. and we can see that the lift force, that basically the sign of the lift force has to be equal to this this acceleration, because we're going to get this force. The sign is going to be along this line right here. The cosine of the lift force actually has to be equal to the weight. And we can take these two equations in the x and the y direction, which we get from these pictures, basically force diagrams, and we can write a vector equation where we have the lift force, the sine theta I in the I hat direction or x direction is going to be added to the cosine in the j direction. That's going to be minus the weight in the j direction, and the result is going to be acceleration in the x direction. So it's basically this visual solution method. VSM is just really a way of writing down a force diagram and going through a step-by-step method to getting the equations and then the vector equation. Pretty similar to what we do already in force diagrams, in my opinion. So the only other thing that we need to understand is that Newton's law applies to a particle. So when we say F equals ma, we're really talking about some sort of particle of mass. And so when we're talking about fluids, and we're going to be obviously talking about how momentum flows, we can note that if we take the time derivative ddt of basically the mass times the volume, that gives us the sum of the forces. And if we sum all over each particle inside a body, each little piece of mass, mi, with its own velocity vi, if we sum up all those together, take the time derivative of it, that is going to equal the total external force existing on the body. So the total momentum of the system is going to be defined as being this capital M, is really just this part here, the sum of all the individual momentums of all the different particles, fluid particles in our fluid or our body under consideration. And therefore we can then write this as the sum of all external forces are going to be equal to the time rate of change of the momentum with respect to time. That also is in a closed system. We're not allowing the mass to go in or out of that. Now this term right here is actually starting to look like the left-hand side of the Reynolds transport theorem, and in fact it is. So we're gonna find out that when we're interested in momentum and applying the Reynolds transport theorem, the left-hand side of that equation in the Lagrangian point of view is just going to be the sum of the external forces. So that's it for section 6.1. I'll be right back with 6.2.